the meetup group, there was a talk that I gave at UTD several months ago, and the first part of this was essentially part of that talk, and it was about an introduction to quantum computing. And so, but I'm really interested in quantum computing and neural computing actually have a lot of commonality in the sense they're both working on hyperdimensional math. And so that's sort of my area where I'm interested in, and I have background in both, so we'll talk about that. So, hang on, let me start this baby here. I'm just recording it. My goal is to, like other YouTube videos that I've done, I record it, clean it up, and then create a clean video with the slides and with all the uhs canceled out, right? So I think I'm recording now, yep. So I've been interested in physics and computing for a long time. In fact, I've been interested in computing since I was in high school, which was in 1968. So I've been programming for 50 years, which that was unusual at the time. People in high school didn't program. So I was one of the early people adopters of learning about how to program. But as a result of that, I worked at Texas Instruments for 25 years. And when I was there, I was interested in sort of like quantum computing and physics. And so like trying to understand the fundamental limits of how you can compute. And it turns out that's related to quantum computing. And so I was the chairman for 92 and 94. And it turns out that there was an 81 conference and a 96 conference hosted by Tom Toffley under the same theme. And so there's only been 4 of these since 1981, and Richard Feynman was the keynote speaker for that conference in 81. You can find the papers for those out in a journal out there. So I got involved with this and learned about quantum computing as a result of hosting these conferences. And so in 1997, I wrote this paper like Will Scalability Sabotage Performance Gains, and it was the lead-off article showing how wires don't scale, and it predicted the multi-core CPUs for 10 years later, and that ended up being the case. It's because wires don't scale, and as you keep going down each semiconductor process, the wires become, essentially things look farther and farther away for the kind of wire that you have. And so as the chip gets bigger and bigger and the gates get smaller and smaller, they actually can't reach to the edge of the gate in a clock cycle anymore. And so then semiconductors aren't integrated anymore, they're actually disintegrating as they get more and more complex. So that was a lead-off article. My website, quantumdoug.com, has a link to that article on there, so you can go find it. And it's sort of required reading for any computer architecture class anymore because it predicts why computer architecture doesn't scale. That's why you're not seeing the big giant multi-scalar computer architecture stuff anymore, because it just doesn't scale. You can only reach smaller and smaller number of gates each process generation instead of more and more gates with each process generation because of this. Ultimately then I got a PhD in quantum computing in 2002. And my advisor was a physics professor working in the engineering department, and so he was a math guy too. And then after that, I graduated, I got a principal investigator for quantum and neural computing, SBIR grant, Small Business Innovation Research, $1 million worth here in Dallas. So this is all stuff I've done in Dallas, believe it or not, since I've been here since 1980. And a bunch of patents filed, in fact, patents on neural and quantum computing as well. So this is a great slide that Babar, and thank him for inviting me to this. He showed me this graph, and I kind of liked it because it's saying, it's talking about here's sort of the traditional view of machine learning, here's the sort of quantum information processing domain, and sort of how they intersect. And I'm not going to go into each one of these, but we're going to talk about some of these concepts like annealing and give you a sense that neural and quantum computing have more in common than you would expect. Like, for example, one of the things about quantum annealing, it actually looks like tunneling, which is a quantum concept, okay? So those are pieces where we're going to find a lot of intersection. Quantum computing is really from physics, okay? It's the intersection of computer science and quantum physics. And it has there's a lot of weird stuff in quantum stuff, okay? And it's because, ultimately, as you keep going down the scale, you keep breaking things down and finally get to the quantum world, and the laws change. And the physicists themselves weren't ready to deal with this 100 years ago. And even Einstein says, spooky action at a distance. He didn't like entanglement. He thought it violated what he thought about relativity. So even in the physics community, it takes a while for them to accept the new meaning of how the universe is actually implemented. And the goal is with quantum and neural computing, we're like at the edge of understanding how even humans might be intelligent, knowing that there's maybe a quantum infrastructure to the entire universe. So, you know, we can go through each one of these, and each one of them is important. I would recommend, like Dr. Quantum, there's a bunch of Dr. Quantum. This is Fred Allen Wolf. He has a bunch of cartoons out there. I'd also recommend PBS Spacetime on YouTube, a bunch of little 10 or 15 minute videos by a physicist, this hunky physicist from Australia, in case the girls want to know that. He's great little 10, 15 minute segments about all these topics, okay? So I recommend, there's a bunch of places out there to learn about this, and then their sponsors for PBS Spacetime are other places to learn. You can actually go in and find out this stuff more concretely, instead of just doing, looking at all the TV channels about it all the time, you know. But one of the things I wanted to share with you is, if you start looking at quantum computing, you realize that there was this famous guy from IBM called Ralph Landauer, and he back in 1961, he says, information is physical. He basically said, if you erase information, you can't ignore it. And the reason you can't ignore it is otherwise you violate thermodynamics. Thermodynamics says you can't destroy or create information. And so you can't, energy. So he says that there's an equivalent energy, a bit is kT worth of energy, and it took until 2014 before they could actually measure this. He was long dead by then. So one of the things you'll learn in this area, in any kind of deep science stuff, like whatever the science is, DNA or whatever, it takes 50 years to figure it out. And some of this stuff, Einstein predicted that there would be a thing called entanglement and Bose condensate in the early 2000, in the early 1900s. It wasn't until 1994 they actually measured the Einstein-Bose condensate, and they were actually, 60 or 80 years later after they did this. So realize that things take 50 or more years for some of these things to happen. But the key is that once you understand that information can erase and affects thermodynamics, then there's a relationship between physics and information, which is good. And in fact, now you start talking about, well, if you don't erase it, what do you have? You have reversible computing, which is the basis of all quantum computing. Everything is reversible. So if you're not erasing anything, you're kind of just, it's a big shell game, you're moving it around, and you're not erasing it, and that's called reversible computing. And if you don't have reversible computing, that's the case of measurement. So you realize that these concepts are fundamental to quantum computing. And you see that there's another relationship between physics and information, because the bit is the smallest increment to a black hole that you can make. So there's this is it from bit. It's John Wheeler from Austin. He was a physicist, and he basically showed that they know that the metric for the surface of the black hole is entropy, but its units is bits, and now they know that the smallest increment that you can make to a black hole is a bit. So you can't, it's discrete, just like an electron is discrete, just like everything else in physics, a photon is discrete. Even space-time itself is discrete. Well, bits are discrete at the black hole level. So, and even quantum foam, it looks like there's nothing in empty space, but as you look closer and closer and closer, the fact that you're observing it causes it to look like it's roiling with energy, and that's called the quantum foam or the zero-point energy. So there's all this deep physical relationship between information and physics, and these are deep. All of these slides we could talk for 10 minutes on instead of 2 minutes. Okay, so realize I'm introducing you. This is a high-level introduction to quantum computing. And so one of the things you realize is that really you have a quantized wave. Everything is this quantized wave. And when I say it's a wave, it's not like a sound wave. It's not like an electromagnetic wave. In fact, it's not even like a gravitational wave. It's a mathematical quantum probability amplitude. It's purely mathematical, it looks like, but yet it affects the physical world. So how is that possible? And so one of the things you have to realize that everything is a quantum state distributed probability waves. And when you think about a wave, you think about it as extending through space, right? But it's everywhere and nowhere at the same time, because the wave is the whole sum of all of its states. So it's hard to get your grasp around that quantum mechanical waves are these mathematical type things that sometimes they look like a particle, sometimes they look like a wave, and you have the double slit experiment here. Double slit experiment here where you send a single photon through, but it acts like a wave because of the apparatus, and you get the interference patterns. This is the famous double slit experiment. So, and then they can start looking at about this. This is Feynman diagrams, and this is how they look at quantum interactions and with virtual particles and everything. So the key is it's a self-consistent whole through space and time. Even if you measure something and it's far apart, it looks like it's like it has instantaneous communications, which is the e-bits, and that looks like it's self-consistent, even though it shouldn't be able to be self-consistent through classical means. But that's the thing about quantum mechanics. It's you can't fake it out. It's self-consistent no matter what you do with it. Okay, and it reflects the measurement bias you use to detect it. So this, where we're looking at a wave property, here we're looking at a photon, a particle kind of property with the photoelectric effect. In fact, this is what Einstein got his only Nobel Prize for. He did all this other stuff, but he got the Nobel Prize for the photoelectric effect. Okay, so there's a lot to particle wave duality. There's great videos out there about this kind of experiment, the twin slit experiment. So you can go and look at that. But what this means is once you have things like probability amplitudes, you can create a phenomena where the barrier is higher than it would be to allow anything to escape through it from a classical sense. But as soon as you look at it as probability amplitude, the probability that particle exists on the other side of the barrier is non-zero. And if you run the experiment, it's over there at that percentage of time. So that's what tunneling is all about, what builds our semiconductors are all built on tunneling. Tunneling diodes and everything that we do is based on tunneling concepts. And in fact, a lot of what happens in chemistry and biology and all this stuff is because of quantum tunneling, that they settle these chemicals at a quantum level. And so that's why they use a lot of quantum mechanics and quantum modeling to do things in the biological and chemistry area and DNA area as well. So, but not only is the position relative, probability like this, but you can think of it as literally a distribution like this. And so you have to kind of start thinking about everything as probabilities. And as we find out in the rest of this talk, that more and more probabilities, the better you can think about visualizing probabilities and probability distributions. And we're going to talk about even a thing called probabilistic geometry, which is everything's probabilities. So it helps from a math perspective if you're kind of familiar with these concepts and talk about it. But the probability that the particle escapes the barrier is non-zero, and so it does. And you have the superposition of both position at both the atomic and the molecular level. They've actually been able to take like a buckyball and show that it's in superposition with itself, and then it collapses back down into a single position. So they actually can do things at a pretty coarse-grained macroscopic level. So talking about how big the macroscopic level is, this was the famous thought experiment by Schrodinger. He had this poor cat who was both alive and dead because of some radioactive decay, and it was in this box. And the question is, if you didn't look in the box, would you know whether the cat was alive or not, or dead? And the answer is, well, it could be in the superposition of both alive and a dead at the same time, and that's why they show it in here. And it's only when you open the box you know which one it is. And so the question is how big does it go? How far up the scale does it go? Okay, and this is still an outstanding issue. I mean, they don't know. They've been trying to determine if there's a threshold for it. And in fact, one of the famous guys, Sir Roger Penrose, he argues that if you have two things and they're in the superposition of position with each other and they both have mass, essentially the mass, the co-mutual mass between the two parts causes it to collapse. And this is his quantum work principle. And he's trying to build an experiment that proves that this is the case, that the collapse is due to gravity. Because the position is in two places, and so it has a mutual gravitational attraction. So these scientists are trying to figure this out at the fundamental level about how physics and even mass and position are all related. Okay? So it turns out I built software that also uses this dead or alive concept. Let's say you have this, you're editing something and it's an atomic edit, but you've done things to it which even affect other things. And then at some point you want to say done, or you press cancel. If you press cancel, that's the cat dead. And if you press done, it's the cat alive. And you want it to be self-consistent with both states until you make the decision. So you can actually apply these concepts to regular traditional software. Just say it has to be in the superposition of both alive and a dead until the decision is actually made, the measurement is made, which is where the guy pressed the button, which button he pushed. Okay? So realize that you can apply this to other areas besides just the quantum mechanical level. You can use it in software design, which is I do. And the Heisenberg uncertainty principle is another famous one. They said, well, the momentum and the position, the change in that has to be bigger than some threshold, which is, this is the Planck's constant here, a standardized Planck constant. And anytime you see Planck's constant, you know it has something to do with quantum, by the way. E is equal to h nu. E is the energy, h is Planck's constant, and nu is the frequency, is the wavelength of the, is the frequency of the particle. So that was an early thing that came out of quantum mechanics, is that h came out of that because of the relationship between frequency and energy in photons, okay? And so h comes in anything having to do with quantum. But what I wanted to show you is that you can only have a certain level of uncertainty. The more you know about the momentum, the less you know about its location. They're like duals in that space, okay? And one of the ways to think about that is you have a sine wave. A sine wave, if you have a single frequency, it starts out as a single frequency like here. A single frequency, it has unlimited expense in time. But if you have a small packet like this requires a lot of frequencies in order to get this state. So you're having a relationship between frequency and time are dual relationships between the extent of time versus the number of frequencies, right? So the same thing is true here. I'm trying to use that as this duality that you can only, that one trades off with the other. And this is a fundamental limit having to do with quantum mechanics. And this kind of says, well, the universe is a simulator and we can't look below the bottom of the simulator. I mean, that's one way to think about it, if that helps you at all. So, but what's interesting is this affects our space-time models, okay? Because time and distance here are there, both energy and momentum also are there. So time and space are there, and that's interesting because those are the main properties of computation. Space is where we store our state. Time is how we make changes to that state. So any computation can be thought of as space-time trade-offs and parallelism about quantum computing. So if quantum physics has fundamentally something to say about how space and time exists, then it changes the way we think about computation as well. So let's talk about the fundamental aspect of qubit. And again, there's a few more slides like this in that other talk that I gave out there. And so I think there was a link put on the Dallas AI website for that link, but you can go to quantumdoug.com as well. And but it's that you take 2 bits, a qubit is really 2 bits. So here you have a classical bit. A classical bit you can think of as a state, and if you represent it as a vector instead of just a binary bit, you can represent it as a vector of +1 like this. This is state 0 and state 1, and you can see that these 2 states, they're mutually exclusive, so they have 180 degrees off. So you can represent them as vectors, and in fact, if you sum them, you get 0. What that sum means, is 0 means, is that it cannot occur. You can't have state 0 and 1 at the same time. So this is a good mathematical concept that comes from a bunch of different areas of math, but it's specifically what I did for my PhD was geometric algebra. And basically we're showing how you can put bits into vector mathematics so that you can now include information theory as part of physics. And so that's kind of what I did for my PhD. But you can now think about a qubit as having 2 states. One here, I don't know if this thing shines very well here, but you have state 0, instead of being down here at 180 degrees, it's only 90 degrees apart. And so now you have a phase angle between them, and some phase angle between them is what a qubit is all about. And at classical bits, the states are mutually exclusive, but quantum bits, the states are orthogonal to each other, and so now you can have phase angles. This is important because now you can get probabilities. So you take that exact same state relationship I just showed you. This is the convention that they show. This is state 0 and state 1. They show it as this notation, which is the Brock-Ket notation. This is the ket. And it's really just an array. This array and this array, they're orthogonal to each other. And so this is sort of, and since these are orthogonal, all you can do is add them. They're like apples and oranges. You can't do anything with, you can't combine them at all. Okay, so this is the superposition. In fact, this is a qubit state in Hilbert space math. And so this is what it looks like. It's actually a 3-dimensional graph like this because it has another angle of phase. But you can think of it as a 2-dimensional graph with a phase angle between it. And this state, in this state, the 0 is not, you have 0 and not 0, and not 0 is over here. So 0, so you invert the state, you go from 0 to 1, it's only a 90-degree angle rather than a 180-degree angle. And they call this spin 1/2 computing. So it takes you instead of inverting it twice, you have to invert it 4 times to get back around to where you are. And this angle here, this moving at 45 degrees and moving at 90 degrees, that is some of the operators that you use with quantum computing. And some of those are reversible, and some of them are not. So this is where reversibility comes up. And this is where the unitarity constraints. These complex coefficients are the probability amplitudes. Their sum of their squares is equal to 1 because they're probabilities. They're actually probabilities, okay? And so these are sort of like the math that supports all of this. And one of the things you can do is you can get this phase angle in here, but you can't peek at it. In fact, you can't even copy it, because to copy it, you'd have to measure it. But if you measure it, you destroy it. Remember the old days when they had core memory? In the 60s, if you read the core memory, the act of reading it caused you to erase the core memory and you have to write it back again. Well, this is what quantum computing is, but it's worse than that, because if you read it, you will get a probabilistic answer. You won't actually know what it was. So this is the basis for the complexity in quantum computing, is this phase angle. If you have an angle that's a 45-degree angle like this, for a state, and you've set it up so it's in this state, and you measure it with respect to 0 or 1, you will get a 50-50 even coin flip every time you measure it. Sometimes it'll be 1, sometimes it'll be 0. Likewise, if you have something that's closer to the 1, you will get essentially the probability, this coefficient, which is essentially this coefficient is this distance here versus this distance here. That probability is the probabilities you get up. So you'll get a 30-60 or a 70-30, 60-40 or 70-30, or a 45-45. That's purely random. So the point is, it's impossible to actually know the state, and so therefore you can't even look at it without destroying it, so therefore you can't copy it, which is called the no cloning principle. So these are fundamental aspects that we are not used to in computer science. We think that we can measure everything and we can copy it. Can't do that in quantum computing. So this is where the probabilities come from. It comes from this phase angle. This is the basis of everything. Both the curse and the power of quantum computing comes from this phase angle here. And it comes from the fact that these bits are spin 1/2 orthogonal dimensions. And there's 2 bits, 2 classical bits if you want to think of it, 2 dimensions that are formed at a 90-degree angle to form this qubit. Okay. So here's the operators for the qubit. They look very different than our AND and NOR gates, okay? In fact, these are the operator matrices. Anytime you have a matrix, anytime you have a Brockett notation, this Brockett notation here we showed you before, you convert that by using a matrix operator. That's the operator for it. And there are hardware pieces that form those operators. So this is a phase shift gate. The unitary gate just means there's no phase change. A phase shift gate rotate by some arbitrary phase. A Hadamard gate rotates by 45 degrees. That's this one here. And the Pauli gates are all the noise gates, and this is equivalent to the NOT gate. So you have both a Hadamard gate, which is a 45 degree, this one up here, 45 degree angle. This switches from 0 to the 45, and then if you apply this again, you get to 1. So if you've gone from 0 to 1, that's the NOT. So this is the square root of NOT. So this is the funny kind of math they use. It says the Hadamard gate is the square root of NOT, knowing that the NOT gate is x. Okay? And so x goes from 0 to 1, or from 1 to 0. That's the NOT gate, and the Hadamard gate goes halfway between, so you have to do it twice. So you can think of operators can be applied multiplicatively, so then if you take the multiplication something twice and you take the square root of it, that's the square root. So this is the weird language that they talk about in quantum computing. It's because of this math. And if you really, this is really weird stuff, and most people aren't used to thinking about it. Even if you've taken a lot of DSP MATLAB stuff, this is still weird, okay? Because it's different kinds of math with different kinds of rules, okay? So there are 2 qubit and 3 qubit operators. You can see that other paper for those. And they're just as weird. Okay, the swap gate, the Toffoli gate, the Fredkin gate, and most of those are reversible. And then the next one is the measurement gate. So if you have a wave function like this, and it's in the probability, so it has some state, and it has some probability, and you measure it, it collapses so that it doesn't have that probability anymore. It's either 0 or 1, and you get a classical pit out of it like this, okay? So they call this a quantum state has collapsed, and they call this the Copenhagen interpretation of quantum mechanics, okay? But measurement gives a probabilistic result. If you take something that's a 45-degree angle and you measure it from the zero bias, you're going to get, and you do it 100 times, you're going to get 50 ones and 50 zeros out of it. So it's probabilistic, okay? And it's based on this relative phase angle. So these are irreversible. If you measure something, it destroys the state. You can't get back to it because you've lost the content of it. This is, anytime you have noise, it's like a measurement, and you call that decoherence. The state now is in a state where you might know what it is, but you've lost the original state that you really wanted. That was the quantum state that you had carefully set up, and now it's gone. It would be like creating a deck of cards, a house of cards like this, and somebody puts the last one and it all falls down. It's the same kind of idea with quantum noise, okay? So this is an important thing to realize, is measurement is part of this process, and it's irreversible compared to all the other gates which can be reversible. And noise, by the way, these Pauli gates are the kinds of noise that you can get. X, Y, and Z, those are the different kinds of noises you can get, and you can get a phase flip, an invert flip, and you can get both a phase and a flip, both of them simultaneously, and those are considered the kinds of noise you can get in a qubit. So a lot of these, because of the noise possibilities in a qubit, some of the people are trying to build quantum error correction where they have more states, 2 or 3 of these qubits together in a specialized subset of those where they can detect if one of them flipped due to noise, and they can automatically fix it. So a lot of people are trying to figure out how to do that kind of thing as well. So once we have one qubit, we can combine them in a specialized way into a register. So this is a single one, and we take each quantum qubit, Q, R, and S, where they're all one qubit, and then we combine them into a quantum register, and it produces, the tensor product is the way you talk about this, and it produces all the permutations of all these states, and we label them as this list. And this list is not all the states that are there mutually exclusive. Those states are all there simultaneously. This is because we have probability, because we have these superposition of states in one qubit, when we combine them, now we get the tensor product states, and this number of states grows with 2 to the n, where n is the number of qubits. Okay? And so this is where the quantum power comes from. And by the way, the sum of the squares of those coefficients are also 1, so you know that they're all probabilities. So if you have a classical register of bits, each bit can be 0 or 1, and so you have 1 out of the possible 2 to the n possible combinations. But if you have a quantum register, it can both be 0 or 1, or some combination thereof, and if you take a quantum register and create a bunch of those, you get all of these quantum states, and you get all 2 to the n possible permutations. And just to see how big this is, if Q is 300 qubits, which is, by the way, the sort of the size that you want to get to before you can start breaking, using Shor's algorithm to break the encryption on that we have for our internet, for our security, you'd need something about this size. 2 to the 300th is more than the number of particles in the known states, in the known universe. So the number of these states, if you sum them up, it would be bigger than the number of atoms in the known universe. And yet, a 300 qubit register manages these states. It's like it has this giant computational state space sitting out there, and it does the self-consistent representation where if I flip one of these qubits, the first one, it affects all of the other ones that are related to it in a self-consistent way. And that's the power of quantum computing. This graph here tells you why quantum computers can solve problems that no other classical computer can solve, because they're cheating. They're not using space-time representations. This quantum state here is outside space-time. In fact, if you have 2 to the 300th unique states, they're all orthogonal to each other. How do you even think about that? So this is really hard for some people to understand, but I wanted to make sure you understood that this is why quantum computing is, and why people are interested in, and why some of the smartest people in the world are struggling to make advances in this, and why it takes anything happening in this area, it takes 20, 30, 40, 50 years to make it happen. Okay, this right here is the slide, this is the moneymaker slide. So 1994, which is almost 25 years ago, Peter Shor figured out this algorithm that you could put as a quantum algorithm, and it uses all these 2 to the q simultaneous states to solve quantum Fourier transform. And this is the block diagram for the quantum Fourier transform. This is the Shor's algorithm, and it relies on this subcomponent, which is quantum Fourier transform. And as you can see, when they make quantum gates, quantum architecture diagrams, this is the block diagram of how you build Shor's algorithm. But each of these, here's the Hadamard gates that we showed you earlier. Here's some of the lower bit registers. This is the quantum Fourier transform, and there's the measurement over there. Okay? They draw circuits as if they were schematics. So if you think you want to program in quantum computing, you have to kind of know how to visually draw out these states. And it basically usually moves from left to right. And so if you look at any of these quantum online systems like IBM's quantum programming system, you'll see a tool that looks like it's a visual thing that you're creating the quantum register, and then you're saying, apply this state next, and then this state next, and this state next, this operator next, and this is what it looks like to program this stuff. But what's interesting about this particular algorithm, it's the killer app for quantum computers, because it solves a problem in quantum polynomial time that no classical computer can solve. And so the whole world went crazy in 1994. Peter Shor came to my conference in '94 and presented about this. And it defined it even defined a new complexity class called quantum polynomial time. And so because of this now, they realized, oh, that because a quantum computer could be built that could run this algorithm, our encryption codes used for the internet were at risk. And so it spurred this huge amount of development in quantum computing, quantum encryption, quantum key distribution, and all this stuff, because everybody's trying to understand about quantum and how to get around the fact that if somebody could build this, then they could break in any internet they wanted to. So this is a big step. Now, I think there's a movie out there, I think it used to be on Netflix, called P versus NP, and it would be, is if you could prove that NP was P, you could do the same thing. So this is like using a quantum computer to solve NP versus NP kind of problems. So can they do all problems with this? No. Can you create a version of the algorithm that Shor's algorithm won't hack? Yes. So people are working on that stuff too. So realize that since '94, everybody and his brother, there's billions of dollars being spent every year by every government, every company, everybody who wants to play anything in this. And you might not know about it because everybody's keeping it quiet because they don't want to give any advantage to any of their competitors. Okay, so this here was the one that broke open the whole quantum. Quantum computing had been around for 20 years before that. Okay, and from then until the last 5 years, nobody could even build a quantum computer. So it took them 20 years just to get started. And now everybody's interested in it because they're actually making progress, but only after billions of dollars being invested by all these companies because they have to build the super cool technology, which D-Wave created, and all this kind of stuff. So just realize that this was a big step in 1994. So remember I was telling you about the software flows? This is how you think about a quantum computer. You have the quantum register, and it's really just 30 or 300 or whatever number of qubit registers, but then you have this quantum controller that keeps changing the state by doing, some kind of interaction with it with photons or lasers or magnetic pulses or whatever to change depending on the implementation. And then they have a regular classical computer to sequence those, okay? And then they get the measurement results. So this is how a quantum computer looks. And I'll show you a picture of some of the quantum computers out there, and that's just the piece down there. This doesn't tell you about all this stuff, okay? And so what you end up having now is the quantum algorithm looks like these block diagrams, and you create these sort of schematics of it. First I do this step, then I apply this operator, then I apply this operator, and then you have to have the compilers, the optimization, error correction codes. You have to convert it all to these control sequences, and then you have to actually have access to a quantum system. You have to initialize it, and then run the algorithm step by step. Not too fast and not too slow, because if it's too slow, it'll decohere, it'll have noise. If it's too fast, it won't actually settle in time. So all of this stuff is black magic, and then you have the qubit implementation on the bottom. So this is like black magic. I mean, you think semiconductors are black magic. This is black magic to the next level, complexity and does it work at all? How do you know if something's that fragile if it actually works? So it's all sub-zero temperature, near 0 degrees Kelvin to keep it all. So So this is just programming, knowing that there's superposition in qubits and quantum registers. But then there's this actual, this is the special thing that they created. They figured out that there's a thing called entangled qubits. Einstein hated it. He called it spooky action at a distance. He was trying to defame it by calling it this weird name. And he called it, in German, there's a specific term that means spooky action at a distance. But basically it says two things that are far apart can interact in a way that violates what we would think about relativity. That's why he didn't like it. And so you can think of it as this, I use this symbol, this symbolic representation here. You can think of as this qubit and this qubit are somehow magically entangled such that even though they're far apart, they're still one acting as one. They're the self-consistent whole. And this is the actual Hilbert space states. Looks just like we showed you in a qubit, except that these are these entangled. This first half of this is from the qubit 0, and the second half of it is from qubit 1. But notice it's a funny state. Instead of all the permutations of 0, 0, 0, 1, 1, 0, 1, 1, 1, it's just these two states. Well, that means that if you measure this, the first qubit will always either be 0 or 1, but if the first one is either 0 or 1, the second one will also be either 0 or 1. They'll be the exact same value, or if you use the magic state version of it, whatever you measure, the other one will be the opposite of it, no matter where it is in the universe. And so this is the spooky action at a distance they talk about. And they have these devices, off-the-shelf devices, that they use for quantum communications now. And they're sending these things down free space, over space. The Chinese are doing it from a satellite. And they're doing it through photon, through fiber optics. And they're using this for quantum key distribution. So this is a real technology. There's probably more patents and technology in this area than quantum computing. And it's been around longer. And you could now have ultra-secure communications between two banks, for example, and if somebody tried to break in and peek, you could find out that they were breaking in and peeking, and they couldn't get the answer because they would be measuring it with the wrong bias, and it would destroy the information, they wouldn't get it. So this is an ultra-secure entanglement system, and they would use it to send the key, and then they would use a classical channel that had the key. So they use it for quantum key distribution. That's how they use entanglement. So they use the key distribution over the secure channel, and then they rotate the key every second, and there's no way you can actually decode a regular key, even if you had a quantum computer, every second. So it ends up being a secure channel, so that's how they do it. But entanglement, the key thing I want to share with you is if you start looking at entanglement, people says, well, it can't really work, and people have been trying to prove that entanglement doesn't really work, but yet it does. And this guy named John Bell was the one who showed it, and now they've really measured it. They know that these entangled states really work. But it's not that hard if you stop thinking about it from a relativity perspective. It's just a four-dimensional space, and it happens to be, we're looking at it from a three-dimensional worldview. So it's easy to think about it when you start thinking about high-dimensional spaces, which I told you is my expertise, is looking at hyperdimensional spaces and its properties. And this is just an example, entire entanglement is an example of it where, by the way, this is a four-dimensional hypercube that's rotating among the different dimensions. So I mean, it's hard to think about it but imagine if we had a 100-dimensional hypercube. You know, it's hard to put your imagination on that. But that's the kind of thing that I work on, and the neural computing part is also related to that, hyperdimensional math. So my research has shown that as soon as you have entanglement, that even space-time itself is entangled, which makes a lot of sense. And so that's one of my papers out there that I did in like 2010 timeframe, is basically showing that once you have a bit view of geometric algebra for quantum computing, you can show that the standard model comes out of that too, that bit representation. It's like, if you were God and tried to create the universe out of nothing, you would use quantum bits to do it because they don't have any mass or energy or space or time yet. It's just like all that stuff is created out of the quantum foam. So the quantum exists before space-time, matter, and energy. And it's like a big bang, but we really think of it like as a big thought. All of a sudden, these quantum dimensions that exist outside space and time started forming space-time, and then they formed the Big Bang and the energy that we know about as the Big Bang. And so this space-time itself, how you think about space-time itself in physics and also in computation is all related to this topic. And so you may be interested or not. I am interested in that kind of thing. And so, but the key is that it comes right from physics, because most of our computation is either time-like, like this, it's inside the light cone, or it's light-like, which means it's on the light cone. But quantum states are space-like. They're a state that exists outside of what you can reach by photons. And so as soon as you start looking at space-like states, you see most quantum states are space-like. If you have 2 to the 300th states, you can't embed them in 3 dimensions. They're somewhere else. They're this hyperdimensional hair that's growing on the universe anywhere we build a quantum register, right? So, so my belief is that space itself and time and even dark matter and dark energy are probably all entangled, and I have the math to show where that supposition comes from. So that's why, that's some of the things that I'm interested in, is like the fundamental nature of space and time, which is related to computational theory, and how it could be related to entanglement. So that's some of the stuff that I'm interested in. So let's get back to a little bit more about quantum instead of quantum physics, quantum computing. These are remember I was telling you that piece of hardware which is the quantum register itself? Well, these are all the pictures of all the different hardware. As you can see, they all look very similar. They're usually hanging down from this equipment like this, and they put this bell jar on the bottom of it to bring it down to cold temperatures, and all the controls are from the top so they can work on it and still cool it and get at it. And this is the view of all of this equipment that everybody's building. And you end up with quantum speed up from this stuff. That's why they're interested in it, because you can get these quantum algorithms, but you also get quantum supremacy, and that is you can't simulate a quantum space beyond a certain size, and that's about 50 qubits, using a classical computer anymore. You actually have to have the quantum computer to do it. Okay, and so everybody is trying to build a universal quantum computer that's greater than 50 bits, and that's the term quantum supremacy, because now you can do something that no classical machine can emulate. So the fastest way to get to the solution for a quantum algorithm is to actually use a quantum algorithm. You can't simulate it anymore. It's too big. I mean, especially if you think about it, you're creating these square matrices of operators, and you have qubits, and you have 50 qubits, so now you have 50 by 50 dimensional matrices that you're applying to these, or 300 by 300, and it's just slow to simulate those things. Plus you have to have all the states involved. So this is the example of, this is a cute picture of the quantum computing race, and everybody's using a different technology. One is using light, and one is using magnetics, and one is using semiconductors. We don't know the actual solution that will be. Everybody wants to build a semiconductor version of this, but not everybody knows how to do that yet. But here's the big thing that ties the two topics together, quantum neural computing. Of these companies that I showed you those pictures for, IBM, Google, Intel, Microsoft, and D-Wave, there's many others too. These are the number of qubits that they're currently advertising that they can build a machine that big. And notice Google has just announced their 72-bit one. IBM is 50, Intel is using 49, and this is the chips. So not only are they working on quantum computing, but they're working on AI and neural computing, okay? So all of these companies don't want to miss the opportunity to be when AI becomes the big thing, or quantum computing becomes the big thing. Okay, and by the way, these slides are going to be put up on my website, so you can see those at the end. So just go to Quantum Doug in a couple days, and this slideshow will be up there. And at some point, I'll probably create a YouTube video of this as well with my comments in it. So the point is that there are many companies that are doing that. And you can see here, this is sort of the race. Somebody created this real cute thing. They want quantum computing, they want high-performance computing, and they want what they call neuromorphic computing or neural computing. These are the different superpowers that all these companies want, okay? And I believe that all of these are trying to build faster and faster algorithms for problems that are exponentially growing. So let's talk about that, what we mean by that. So this is all having to do with hyperdimensional landscapes, okay? So if you look at what a neural network looks like, it looks like this. They have usually an input tree, and then they have 2 to 10 to 12 levels of these hidden layers. And then what they do is they program this by sending input data in here, optimizing the weights in all these networks so that you optimize this function that you're trying to get out of the outputs so that it matches, right? So this is a hyperdimensional landscape, and you're trying to find the minimum on it for the weights so that the weights represent the sum, the optimization of the sum of all the input data such that you give the answer that you're looking for, okay? So it looks like this. You actually have a hyperdimensional version of this where you have peaks and troughs, and a regular thermal annealing process that you would use for a lot of these regular systems are using thermal annealing, they want to go over these minimums, these little hills like this, and quantum annealing goes through it by tunneling. So this is a sort of an annealing, a way of thinking about this landscape, hyperdimensional landscape, but realize that this is a weighted sum of the sum of all, each node here is the weighted sum of all the input data for that node. So it's like a hologram. It's like a hologram that's multi-level, okay? But you can actually think about a hologram too, is if you have a reference point and an object, then each point on the film is the weighted sum of all the image from all the points that reflected off of that light. And so they're all at a different amplitude. You get this amplitude here on the film, and then if you look at that amplitude and you generate the incident wave again, then you get the object projected out there because it shows back up as the reverse of this transform. Well, that's what we're doing with all of this stuff. It's all a transformational kind of thing that all has these sums in there. These sums up here, up in the corner here, it's the sum of all these weighted components. So you can think of all of this math as hyperdimensional sums and hyperdimensional landscapes. And so it helps you figure out what they're actually doing if you take it from that perspective. Here on the bottom here, this is Numenta's hierarchical temporal memory. It's using a version of neural networks that's equivalent to a technology that I worked on, correlative theory. And they basically, the guy who's the founder of Numenta used to be the founder of, blocking on the name of the company, Palm Pilot. And so he sold Palm Pilot, made a bunch of money, went and reinvested it back in neural computing. And he basically says, if you're not using hierarchical temporal memories, which is a variation of sparse distributed coding, if you're not using that, you're not doing AI. And the reason for it is because that particular kind of mathematics, sparse distributed coding and content addressable memories, has additional mathematical properties like quantum properties have. It has superposition in it as well. And it has properties in it that you can't emulate if you're not using that math. So it's a natural math system to solve this class of problems, and it's a hyperdimensional math. I happen to work in that neural and quantum computing thing. That's what we were working on, quantum computing and neural computing using sparse distributed coding. That's what I worked on for 3 years and got $1 million from the government to go build. So these things are all related to these weights. And let's see here. So let's talk about what this hyperdimensionality is. I call it, if you look on Wikipedia, you see there's a thing called curse of dimensionality. It's actually, yeah, it's a thing out there. As the number of D features or dimension grows, the possible subsets grow exponentially as 2D. Well, the problem is if you're trying to form a cluster, essentially you're creating a subset of a set of features. And in order to do that, you probably need to know which dimensions you want to include or exclude because the number of dimensions is too big otherwise. And so trying to find an efficient algorithm that scales with respect to knowing, without knowing the number of dimensions and has an arbitrary number of D, you can see the subspace grows really big, okay? So there is no efficient hyperdimensional version of radar or sonar or density metric algorithm. There just isn't. Like if we have radar in the three-dimensional space, it's not, we don't have to have the radar computationally look at the entire universe to work. It only works locally, right? There's a locality to the radar signal or the sonar signal. So we don't have to have huge computational complexity proportional to the size of the space. But when you're simulating some of these things, you're essentially looking at the entire space all at the same time, and so your computation can't be easily broken down into parallelism because as the space grows, now your computation is proportional to the size of the space, not proportional to the amount of locality you want in the space, okay? So, but what happens is as you start looking at this, here's a little diagram on the bottom here, where here's that hyperdimensional cube again. You go from 1 dimension to 2 dimensions to 3 dimensions to 4 dimensions, and pretty soon you end up with a hyperdimensional cube, and you start seeing these probabilistic geometries. This is a non-intuitive geometry. If you take two random points in high dimensional space, P and Q, and this is a qubit, and you normalize it, then this is the dimensions you get, and you find out that between the center of the space, that you can normalize it by that distance metric, and you find that all points in this randomly generated space are orthogonal to each other, which is great. That means they're codes. They're unique codes and nobody's near them. But that means that this is a probabilistic geometry, and that if two things are near each other, they represent information. Two things that are very far apart are random and they don't represent any information. So things that are naturally clustered in this represent a kind of high-dimensional radar, and those show up as things that are near each other and mathematically related and represent information content. And the good news about this kind of mathematics, that this is the same thing that Numenta's using, is that there's a built-in yardstick that represents, it's like the speed of light. You know how big the speed of light is, so you know how far is something compared to that. Well, this has a built-in metrics that says this is essentially the effective distance for random things, so you can compare everything to that yardstick. So this, if you are using anything that has 100 or more dimensions in it, there is a built-in standard distance and standard radius. You just might not know that it exists, and you can use that to determine how far things are apart using that as a standard metric. So this is the kind of things, again, that I'm thinking about. So the point is that these points spread out in a hyperdimensional volume. That this, you can say this many different ways, but it shows up in a black hole too. There is no inside to the black hole, it's a singularity. All the points in a black hole are on its surface. And that's due to the math as well as the physics. If you look at the volume of any hyperdimensional structure, all the volume is on its surface area. And it's because the points are all spread out. The distance between any two points gets bigger and bigger and bigger the more dimensions you have. And so all the points are spread out and they're all on their surface area. Again, very unintuitive math. This is just from the math of high-dimensional spaces. This doesn't even have to do with the math of quantum physics. This has to do with the math of high-dimensional spaces. So most people aren't even aware that this stuff exists, and that's why I'm talking to you about it. So, but one thing is interesting is the similarity measures look like distance metrics in that. And so you can use what your intuition about distance measures, even though they fail you because it's the high-dimensional space, and they have non-intuitive geometries. And so essentially searching for an answer is just saying which point in the high-dimensional space represents the answer to my problem, and finding that can be big if the high-dimensional space is very big. Okay? And it requires a lot of parallelism, and quantum computing can give you that parallelism. Okay? So this is a deep topic. It's recursive dimensionality, and it's why all the problems that we care about in AI and quantum computing and neurocomputing grow with 2 to the d. And they're all exponential problems. So we need as much horsepower as we can to solve those problems, okay? So how do you visualize these hyperdimensions? I try to use these like pickup sticks, and every pair of dimensions represents this dimension. It's like a bit. And pick any two, and they're orthogonal to each other. So you can't even represent it in 3 dimensions or 2 dimensions. It's hard to visualize this. So you can only visualize it like this. This is how I visualize it, is you have a hypercube, and you randomly pick points in there, and all random points are all equal distance to each other. It's a high-dimensional version of a tetrahedron. Okay, a tetrahedron is nothing more than a 3-dimensional equilateral triangle, right? Well, imagine a hyperdimensional version of that, where all points are equal distance to all other points, and they form this thing. It's not a sphere, it's a tetrahedron, hyperdimensional version of tetrahedron, and that it has a midpoint of that, and that's what the standard distance and standard radius is all about. It's the structure that naturally forms anytime you have 100 or more dimensions. Actually, it forms anytime you have 20 or more dimensions. So this is what you can think about it is, this is how we have to visualize it, and points to show up there probabilistically. This is called a probabilistic geometry. By the way, both of these cannot be embedded in 3 dimensions or 2D hologram. Entanglement, you can map it to a 2D surface area for a hologram, but it doesn't represent the non-local requirement that entanglement does. So this, trying to reduce the dimensionality, is just a computer science trick so they can get a handle on the growth of the problem. But you can't do it. You actually have to believe that those dimensions exist out there, especially in the quantum world, where every E-bit doesn't interact with every other E-bit. They only have their own private 4 dimensions. So every E-bit has their own private 4 dimensions. Otherwise, they would collapse on each other. And so you can't reduce the dimensionality of this problem. So this is important to know because now we're going to start talking about sort of the advantages and disadvantages of using quantum for AI. And the big one is quantum dimensions are real. They're not simulated. Which means that that's why you get the quantum supremacy. You get the efficiency. You're using a natural representation from physics to get maximum computational parallelism and properties that you can't get just by simulating it. you can have an AI that's simulated, but it takes 1,000 years to get to the answer. That doesn't help when the tiger's ready to bounce on you, right? You have to know to do it instantly. So this is important. Real versus simulated affects supremacy. Also, quantum superposition entanglement probabilities, there's variations of this are possible in neural networks, for example. So there is actually superposition in probabilities in neural computing as well. It's sort of the macroscopic view of what you see in the quantum domain. Those things you can't see in any place else but in quantum physics. Okay? And quantum speedup over clusters, they now know that there are quantum algorithms. And that Shor's algorithm is an example, Grover's algorithm other. Now they're finding many other ones. You can find a list out there on the internet of all the algorithms that have quantum speedup. That means that they outperform the classical version of that because they do things in parallel and they usually get a square root of n faster than the classical algorithms do. Okay? But also you get quantum parallelism. Not only you get the speed up, but you get the parallelism because you're having all of these states being simultaneously operated on in parallel at a giant state space. And that we can't simulate either. Okay? So, and it's self-consistency across space-time. So that's what entanglement is all about. And in fact, it enables you to solve different complexity classes. So quantums definitely has advantages for all those things, especially if you're dealing with state spaces that are exponentially growing. Then you need that power to do that. So what are the quantum disadvantages? Well, first of all, there's no cloning, there's uncertainty, and there's noise, and there's measurement bias. It's extremely exotic hardware and unlimited access. There's not very many quantum machines out there. There isn't anything bigger than a 72-bit quantum computer right now. Okay? There's no long-term storage in the quantum. You can't store stuff like a database in there. So you have to essentially funnel all of your stuff into there, do the operation, and then get the answer out, and then it's gone. It's the house of cards. And so there's no long-term state storage in there. So anything that needs long-term, you won't replace databases anytime soon with quantum computers. So you don't have to worry about that. So need for quantum error correction, of course we need it somehow, either by just reducing the noise of the whole system or using quantum error correction techniques. So it's not clear how to build a universal quantum computer. I mean, D-Wave says they have a quantum computer that has 2,000 qubits in it, but it's a simulated annealing machine. It doesn't do Shor's algorithm. It's not a general purpose universal quantum computer. You can't run Shor's algorithm on D-Wave. Is it useful? Yeah, Google bought one, and then they're building their own in addition to that. Okay, so in fact, if you're interested in that job, there was a job offer in Fort Worth at one of the companies over here that says go learn to program D-Wave and go support their D-Wave job in quantum computing over in Fort Worth for one of the military contractors. So if people are interested in doing this stuff, hey, I could have gone and done that if I wanted to move to Fort Worth, but I didn't want to move to Fort Worth, okay? So I also don't want to move to Vancouver. My wife might want to move to Vancouver with Trump being president, but that's a separate thing, you know? So steep learning curve for the quantum algorithms math. That's another problem. A lot of people just don't have that math, okay? And essentially you have to choreograph the quantum interference patterns to get the AI algorithm. So they have to match what you're trying to do with the problem to the quantum things that you can do on the quantum hardware. And that's what they're trying to do. And you know, here's some books you can find out there. I mean, these are just the two first ones that came up kind of thing. I'm not recommending them necessarily, but you may find that people are trying, whether they call it quantum machine learning or quantum artificial intelligence or whatever, they're trying to tie these relationships because this is really a hard problem and it's not clear what the key applications work on first. So it seems like the advantages would far outweigh the disadvantage, but the disadvantages make it really hard to think, oh, why would I do this, right? But yet people are spending billions of dollars on it because they're interested in both in quantum computing and the effect that you can get from quantum computing, the upper top of this, to help them solve the AI problems that they know don't scale well either, okay? So let's talk about the last thing, elephant in the room. I call it the myth of AI. Okay, in the 1960s, when at MIT and stuff were working on artificial intelligence, Lisp machines and Prolog and those kinds of technologies, they were all promoting to the government, and anybody who would fund them, they would say, in the next 10 years, we will have general artificial intelligence using some technology X, whatever they were promoting, okay? And this helped them get funding, okay? And AI researchers have been predicting this for 60 years, continuously for, you know, in 10 years, okay? Well, the problem is in 10 years we're going to be near the limit of Moore's law for semiconductor scaling. And we still, only beginning now, things like AlphaGo and deep learning stuff, we're starting to get an inkling, but they've been saying this for 50 years, okay? And if you go look at what's happening, it's still very narrow. It's not general AI, general artificial intelligence, okay? And one of the things that I keep saying, well, why is that? And I think that part of it is AI assumes that real intelligence is due to a classical brain. But if you looked at what the intersection in between these big complex algorithms and AI and quantum, if you had a quantum system, you could outperform a classical system, and maybe AI falls into that classification as well. So, I mean, I just trying to make it obvious that people assume that real intelligence is due to a classical brain. And so, deep learning appears to be useful and effective, AlphaGo and machine translation and all that, but they're not sure how deep neural nets really work. They know it's this weighted sum. They said they modeled it after neural networks, but they don't really know how it works. They really don't. And they don't, and because for a long time they were saying, oh, let's do 2 levels, or let's do 3 levels, let's do 4 levels. Well, now they're up to 12 or more levels, 15 levels, and now they're getting good results, but they have to do big data in order to, they have to big computational data in order to program and to get this trained, and then it's starting to produce useful effects. But the real question that I like to ask people is, well, does AI have any meaning? I mean, it might know how to beat the guy in Go or in chess, but it doesn't know about chess. It doesn't know the meaning of these moves. It doesn't know the meaning of that. And this is what's called the Chinese room. The Chinese room is you have a room as the input port and output port, and there's a guy in there who's getting Chinese symbols, and he looks up the Chinese symbols in this dictionary, and then he knows to go use this output for when this input comes in. And so think of that as machine translation, right? And so, but we don't know what the symbols mean. It's people who might know Chinese, you can pick a different language. Most people in the US, when we give them this example, they don't know what Chinese is. So it's just this meaningless translation going on. And that's part of the problem is, I'm a computer programmer. My job depends on meaning. To understand the requirements, to represent the use patterns, to write the code, to come up with the test cases, to know when something breaks, why that happens, the meaning of the error. We can't do any of that with AI. So a friend of mine was saying that most of what we're doing with AI right now is this very narrow application, even as something as narrow as AlphaGo, winning AlphaGo. It's very narrow compared to the general intelligence that a 2-year-old has, okay? So there is no meaning. So if you think you're using the word semantics and you mean semantics is exactly equivalent to meaning, that's a fallacy, it's a category error. Meaning and semantics. Semantics is the study of meaning, but it doesn't actually mean meaning. Okay? So realize that everybody's using this fancy word semantics thinking they're talking about meaning, but they're not. There is no meaning anywhere here. If I look at a chair, I project the meaning of the word chair, the thought of the meaning of the chair to the chair. But the chair itself has no intrinsic meaning by itself. If, you know, 8-legged alien came down, they wouldn't know what that chair was. They wouldn't have any meaning about that chair. It's only us and humans that we have that meaning. So meaning is important to me because I'm going, well, where is the meaning, you know? And I think a lot of this hyperdimensional math I'm doing is starting to look at content addressable memories and similarity matrix, and you could think about, you could probably get meaning of something like that. But again, it requires an actual hyperdimensional space instead of a simulated hyperdimensional space to make it efficient. So I talk about quantum and correlithms is the name of that technology, that neural network kind of thing that, that Numenta is working on. They're both hyperdimensional. So you have to start thinking about hyperdimensional math. And are these real dimensions actually required for efficiency and scalability rather than simulating it? You can only go so far in quantum systems to simulate them in a classical system. Well, AI may be that kind of system that you naturally need quantum systems to do AI efficiently. And I don't know the answer to that. That's more of a question than a statement. So, but anyhow, you end up with probabilistic cloud states at all levels of the hierarchy, and you probably end up with space-like states that you can't simulate using classical computing or harness inside 3D. So quantum-based AI may have revolutionary advantages, and again, the question I ask on the bottom here is real intelligence classical or quantum? I mean, that's part of my particular bent, is looking at that problem. Is it classical or quantum? And I don't know the answer to that, but I'm asking the questions and trying to get other people to think about that. So here's my conclusion slide, and hopefully in a reasonable time frame here. But AI and quantum both challenge computer science, which is good. You know, they both use hyperdimensional mathematics. They're both trying to efficiently solve these really complex algorithms. They both have exponential growth of the algorithms and the data structures associated with them. Both rely on extremely concurrent infrastructures. You know, and that's why they're building all these fancy MapReduce infrastructures and all the concurrent systems. They both rely on probabilistic solutions. They both exhibit quantum-like properties like tunneling and phase angles and nearness properties. And quantum and AI may force us to ask these hard questions about what is quantum, what is computing, what is the physical nature of the reality, and force us to think about space-time itself differently, which is the fundamentals. So really, researchers are really trying to begin to find these connections, and that's why I think this slide kind of sums up. It says, who knew that all these hard questions were being dealt with by the people who were working in these two fields? But they're basically having to challenge everything that they thought was firm ground, and they're having to rethink it all. And that's the same thing that's going on with quantum physics over the last 100 years as well. So we're going to go to question and answers. I'm just seeding these questions as a kind of thing that I like to think about. Where does meaning emerge from brain randomness? How does space-time emerge from the quantum? How does consciousness emerge from the brain? There's whole conferences for 15 years on consciousness and the special thing about consciousness. And I would put meaning and consciousness in the same. So if you don't like the word consciousness, put the word meaning in there. How does a meaning emerge from the brain? And this is the slide that's on the Dallas AI website here. And so I just put it up to remind you that you're at the Dallas AI meeting. And thank you all. If you have any questions, let's hear them now. Thank you.
Okay, when you were talking about one of the limitations and disadvantages, you mentioned the exotic hardware.
Yeah.
And is it because of power restrictions?
Low temperature,
yeah.
Noise.
Okay, and what
And there's very limited numbers of those. You can see those. That had all that exotic hardware hanging. You know, that looked like a science fair experiment. Yeah, those things are all. You can go see more pictures out there on that.
So what's the biggest problem? Is it like the power and the?
It's not power. It's controlling noise, and they have to have very low temperature. And so, I mean, D-Wave actually helped the whole industry because it promoted figuring out how to commercialize these that were used to be in physics experiments. Now they're trying to do it in computer labs, right? These low temperature cryogenic systems that they can interface with through radio frequency stuff and light and photonic stuff. So it's a big technological challenge to integrate the hardware, the semiconductors, the low temperature stuff, and then the control signals, and make sure that they can get something out of it rather than just noise all the time. So.
Oh, I get it. Okay, thanks.
So in your opinion, how long before we have a general purpose quantum computer? I mean, you say it could be used for the AI use cases. I'm thinking about my passwords.
Yeah,
I can just take my passwords or any encryption key very quickly.
Right, and the government's been worried about that too. You know, it may be that the government has already solved this problem and hasn't told anybody. So be paranoid about that too, if you were paranoid about things. But I don't think that that's happened because it's too hard of a problem. But I do have this slide here that I put some other slides that I put together. Here's an example, quantum version of Moore's Law. Okay, the only thing I don't like about this graph is that it started in 2016. Well, they've been working on quantum computing for 20 years before this. Where is the 1-bit and the 2-bit? They didn't follow Moore's Law for the first 20 years. So this is not a representative thing, and it might be representative going forward. But the problem is that you need 1,000 qubits here before you can start solving this. And so this predicts that in order to get 1,000 by 2020, you should have a stronger password somewhere. So if that's the case, if you can run Shor's algorithm on a 1,000 qubit machine, then probably the internet will go to higher encryption codes. Instead of 256 or 1,000 bit, they'll go to 4,000 bit so that they can't crack this. So, okay. I mean, I have a bunch of slides here that I just put aside because I had too many. So, but that was an example of one that I thought was interesting. So, any other questions? I mean, if we don't want to answer questions in this, we can just have one-on-one conversations at the end too. So. It's okay, I can hang around a little bit until he kicks us out of here. And so, and he said, what time did you say that we have to be kicked out of here? 8 o'clock. Yeah, okay. So.
US, any other countries in terms
Yeah.
of quantum computing?
Yeah, Japan, China is way ahead on entanglement. They have quantum key distribution networks that are on photonics all over the country, and they're trying to do satellite stuff with quantum entanglement. And so they're sort of the leader right now. Even though US had the early advantage in it, they decided that they wanted to beat the US in that. So yeah, they're well, I mean, it's a bigger country. It's got 3 times as many people on it. And so I don't see India. India's working on it too, but I don't see them as like the Chinese. But all the European countries. I mean, there's on my other talk I gave, I show a chart of all the different companies that are working in this area and all the different countries and companies and institutions. I mean, billions and billions and billions of dollars being spent on this. So.
Yeah, Vice News had a really good episode on Chinese using the satellite.
Oh yeah.
The laser communication.
Oh nice.
It was pretty cool.
Which one on the?
Vice. It's a.
Okay.
Yeah. I can't remember the episode number, but it was last few weeks.
Okay, cool. Yeah, I mean, there's a bunch of YouTube stuff out there too, so you just have to figure out which one meets your needs for how long it is.
Wives usually post their stuff on YouTube as well, so.
Yeah, okay. So, any other questions? I mean, does anybody feel like they have the math skills for this? I don't either. I don't either. Okay, so that's when I said this same talk a couple months ago to UTD, I said you as students need to realize that this is really deep math. And so you as students should go study the math if you want to be employed in quantum computing. And right now, employment in quantum computing, they can't find enough qualified personnel for this, okay? Canada is producing, there's these institutes in Europe, in UK, in Canada, that are specifically centers for quantum computing, and they produce these students that are the top students in the world for this area, but there's not enough of them. So is Dallas, UTD, and SMU both have some programs, but they don't even have a full-time person for quantum computing at UTD. SMU is trying. There was some SMU-related quantum computing stuff in the newspaper over the last 6 months, so you can find that there's some activity in Dallas, but Dallas is nowhere near. It's embarrassingly bad a hotspot of quantum computing stuff in Dallas.
Hi, Professor. Would you like to explain a little more about the quantum logic and why it is important?
Quantum noise, yeah. If you have this qubit, remember it's this phase state, and I said the noise shows up as either a flipping of the state or a phase angle change or a both flip and phase angle change. So what happens is what starts out here is the state, and you want it here because that's the real result, that is the result of the state that you're in, but all of a sudden it flips over here and it adds noise to it. So it may be that the whole it's like creating a 1-bit error in a program that's talking to the database. It won't run anymore. So it'll just not work. And so noise, it's very sensitive to noise, and trying to keep the noise for these systems where they can keep the system without noise being injected for a long enough period of time to run the computation is a problem. That's what they're concerned about. So.